The IEEE Green Book, IEEE Standard 518, provides separation recommendations for electrical installations. For industrial applications, power cables of all voltages should be separated from instrumentation cables by a minimum of 300 mm, which is approximately 12 inches. Alternating current power cables should be placed above direct current power cables to minimize inductive interference. When using trays for power and direct current instrumentation cabling, maintain a minimum separation of 150 mm, about 6 inches, between the two types of cables, both laterally and vertically, if possible. Allow a minimum clearance of 75 mm, or 3 inches, between the cables and the edges of the tray. If feasible, consider using separate compartments or dividers within the tray to physically isolate the two types of cabling. Twisted, shielded cables can provide additional noise reduction compared to unshielded cables. Select shielded cables for all instrumentation circuits. Ensure that the cable shields are properly grounded at both ends. Avoid mixing multiple signal types, such as analog, digital, and thermocouples, within the same shielded cable. Keep shielded cables away from sources of electromagnetic interference, such as power cables and transformers. While specific separation distances may vary depending on the application and equipment, the general guidelines provide a reasonable starting point. By following these recommendations, you can minimize the risk of noise and interference between power and direct current instrumentation cabling in industrial environments, ensuring reliable and accurate signal transmission. Firstly, consider the voltage levels involved. Higher voltage power cables will induce more noise than lower voltage ones, thus requiring greater separation. Secondly, consider the sensitivity of the instrumentation circuits. Highly sensitive circuits require greater separation or better shielding. Thirdly, assess the electromagnetic environment. Areas with high levels of electromagnetic interference require greater separation and shielding. Fourthly, evaluate the type of cabling used. Shielded twisted pair cables offer better noise immunity compared to unshielded cables. Fifthly, consider cable tray construction. Solid bottom trays provide better shielding than ladder-type trays. Sixthly, consider the grounding practices. Proper grounding is essential for minimizing noise and interference. Seventhly, consider the routing of cables. Avoid running cables parallel to each other for long distances. Eighthly, consider the physical layout of the facility. The physical layout of the facility can impact cable separation requirements. Ninthly, consider local codes and regulations. Local codes and regulations may dictate minimum separation distances. Tenthly, consider consulting with a qualified engineer. A qualified engineer can provide guidance on cable separation based on the specific application and environment. Proper grounding is crucial for effective shielding. Grounding the shield at both ends can create ground loops if not done carefully. An alternative is to ground the shield at only one end, typically the source end, to prevent ground loops while still providing shielding. Verify the grounding system's integrity to ensure it effectively carries fault currents and minimizes noise. The type of signal being carried by the instrumentation cable also influences separation requirements. Analog signals are generally more susceptible to noise than digital signals. Thermocouple signals, being very low voltage, require even greater care in shielding and separation. High-frequency signals also require more careful consideration due to their increased susceptibility to interference. Power cables generate electromagnetic fields that can induce currents in nearby conductors. The magnitude of the induced current depends on several factors, including the current in the power cable, the distance between the cables, and the frequency of the current. These induced currents can cause noise and interference in instrumentation circuits, leading to inaccurate readings or malfunctions. Shielded cables provide a barrier against electromagnetic interference. The shield, typically made of copper or aluminum, surrounds the inner conductors and is connected to ground. This creates a Faraday cage effect, preventing external electromagnetic fields from inducing currents in the inner conductors. The effectiveness of the shield depends on its conductivity, thickness, and the quality of the grounding connection. Twisted pair cables further reduce noise and interference by twisting the conductors together. This twisting action cancels out electromagnetic fields induced in the conductors, reducing the overall noise level. The tighter the twist, the better the noise immunity. When routing cables, avoid running them parallel to each other for long distances. Parallel runs increase the opportunity for electromagnetic interference to couple from one cable to another. If parallel runs are unavoidable, maintain the maximum possible separation distance and consider using shielded cables. Crossing cables at right angles minimizes the coupling of electromagnetic fields. Consider using cable trays with dividers to physically separate power and instrumentation cables. Dividers provide an additional barrier against electromagnetic interference and prevent accidental contact between cables. Solid bottom trays provide better shielding than ladder-type trays, further reducing noise and interference. In some cases, it may be necessary to use conduit to provide additional shielding and protection. Conduit is a metal tube that encloses the cables, providing a barrier against electromagnetic interference and physical damage. Separate conduit should be used for power and instrumentation cables. When installing cables, avoid sharp bends and kinks. Sharp bends can damage the insulation and increase the risk of shorts and ground faults. Follow the cable manufacturer's recommendations for minimum bend radius. Properly support cables to prevent sagging and strain. Sagging cables can put stress on connections and increase the risk of damage. Use cable ties or other support devices to secure the cables to the tray or conduit. Label all cables clearly and accurately. Labeling makes it easier to identify and troubleshoot cables, reducing downtime and improving safety. Use a consistent labeling scheme throughout the facility. Regularly inspect cables for damage and wear. Damaged cables can pose a safety hazard and increase the risk of noise and interference. Replace damaged cables promptly. Keep cable trays and conduits clean and free of debris. Debris can accumulate in cable trays and conduits, creating a fire hazard and interfering with cable cooling. Clean cable trays and conduits regularly. Ensure that all electrical equipment is properly grounded. Proper grounding is essential for minimizing noise and interference and preventing electrical shock. Test grounding systems regularly to ensure they are functioning correctly. Follow all applicable codes and regulations. Electrical codes and regulations are designed to ensure the safe and reliable operation of electrical systems. Adhere to all applicable codes and regulations when installing and maintaining cables. Consult with a qualified electrical engineer for assistance with complex cabling systems. A qualified engineer can provide guidance on cable selection, routing, grounding, and other aspects of cabling system design. Consider using fiber optic cables for instrumentation signals in electrically noisy environments. Fiber optic cables are immune to electromagnetic interference, providing a reliable and noise-free signal transmission path. However, fiber optic cables require specialized installation and termination techniques. Regularly review and update cabling practices to reflect changes in technology and industry best practices. Staying up to date with the latest cabling practices can help ensure the safer and reliable operation of electrical systems. Document all cabling installations, including cable types, routing, grounding, and termination details. Documentation makes it easier to troubleshoot problems and maintain the system over time. Store documentation in a safe and accessible location. Train personnel on proper cabling practices. Training can help prevent mistakes and ensure that cables are installed and maintained correctly. Provide regular refresher training to keep personnel up to date on the latest practices. Use appropriate tools and equipment for cable installation and termination. Using the wrong tools can damage cables and compromise their performance. Invest in high-quality tools and equipment. Follow manufacturer's instructions for cable installation and termination. Incorrect installation can damage cables and void warranties. Read and understand the manufacturer's instructions before beginning any work. Use cable glands to seal cable entries into enclosures. Cable glands provide a secure and watertight seal, preventing moisture and dust from entering the enclosure. Select cable glands that are appropriate for the cable type and environment. Use surge protection devices to protect instrumentation circuits from voltage surges. Voltage surges can damage sensitive electronic equipment. Install surge protection devices at the power source and at the equipment being protected. Consider using uninterruptible power supplies, UPS, for critical instrumentation circuits. A UPS provides backup power in the event of a power outage, ensuring that critical systems continue to operate. Select a UPS that is appropriately sized for the load. Implement a regular maintenance program for cabling systems. A maintenance program should include visual inspections, testing, and cleaning. Regular maintenance can help prevent problems and extend the life of the system. Keep spare cables and components on hand for emergency repairs. Having spare parts readily available can minimize downtime in the event of a cable failure. Store spare parts in a clean and dry location. Establish a clear chain of command for cabling system issues. Knowing who to contact in the event of a problem can help resolve issues quickly and efficiently. Communicate effectively with all stakeholders about cabling system issues. Communication can help prevent misunderstandings and ensure that everyone is on the same page. The separation of power and instrumentation cables is crucial for ensuring the reliable and accurate operation of industrial equipment. Following the guidelines outlined above can help minimize noise and interference, preventing malfunctions and downtime. Remember to consider the specific application and environment when determining cable separation requirements. Consult with qualified professionals when necessary. The 480 volts alternating current 3-phase motor leads can induce significant electromagnetic interference. The 24 volts direct current transmitter wiring is particularly susceptible to noise. The combination of these factors necessitates careful attention to cable separation and shielding. In tray applications, maintaining the recommended 6 inches separation both laterally and vertically is important. Using separate compartments or dividers within the tray provides an extra layer of protection against interference. Twisted, shielded cables are highly recommended for all instrumentation circuits, especially those carrying low voltage signals. Ensure the cable shields are properly grounded at both ends to maximize their effectiveness. Avoid running multiple signal types within the same shielded cable to prevent crosstalk and interference. Keep shielded cables away from sources of electromagnetic interference such as transformers and other power equipment. The steel conduit provides excellent shielding, which is why separate conduits for alternating current and direct current circuits are a common practice. However, cable trays do not offer the same level of shielding, so additional measures are necessary. These measures include physical separation, shielded cables, and proper grounding. The goal is to minimize the coupling of electromagnetic fields between power and instrumentation cables, ensuring the integrity of the instrumentation signals. Regular inspections and maintenance are essential for verifying the effectiveness of the cable separation and shielding measures. Periodic testing of the instrumentation circuits can help identify potential problems before they lead to malfunctions. Consider using spectrum analyzers or other diagnostic tools to measure noise levels in instrumentation circuits. The results of these tests can be used to fine-tune the cable separation and shielding measures. Remember that cable separation is not a one-size-fits-all solution. The optimal separation distance depends on several factors, including the voltage levels, signal types, electromagnetic environment, and cable types. It is important to carefully consider all of these factors when designing and installing cabling systems. The use of high-quality cables and connectors is also essential for minimizing noise and interference. Cheap or poorly made cables and connectors can introduce noise and degrade signal quality. Invest in high-quality components to ensure the reliable operation of the cabling system. Proper installation techniques are also crucial. Incorrect installation can damage cables and compromise their performance. Follow the manufacturer's instructions carefully and use appropriate tools and equipment. Training personnel on proper cabling practices can help prevent mistakes and ensure that cables are installed correctly.